So here's a picture of Saturn's rings, but it's backlit. So our probe, Cassini, is looking at Saturn, and the sun is actually just behind Saturn, illuminating the rings. And Saturn, by far, has the most gorgeous rings around any planet that we've found, but it's not the only planet with rings. Okay. Uranus has a faint ring system. Neptune has a couple of small rings. And Jupiter, again, it's backlit, so here's the edge of its atmosphere. Here's the rings. So all of the Jovians have rings, just Saturn's are the only really obvious, really beautiful ones. The rings are made up of particles, and the particles range in size from tiny little grains all the way up to boulders. And each particle orbits the planet according to Kepler's third law. So the innermost moons and the innermost particles would travel the fastest, and the outermost moons and particles would travel the slowest. And the particles are always going to be bumping into each other, and that's going to shatter them and break them down. So over time, rings get less beautiful. Over time, rings lose particles. Also, most of these particles are going to be ice, and ice can get a little bit less reflective the longer it's exposed to space. Rings are formed by debris, and the debris usually comes from collisions with the Jovian's many moons. Right? And the moons are mostly ice, so you get a lot of ice debris. And the debris will fill out to have a beautiful ring system. So the reason why Jupiter's rings probably are not that gorgeous is either it was a small collision with very little debris, or the collision happened so long ago that not much debris is left. Okay. Here we're going to pan to the side so we can see Saturn's rings edge on. You'll see several moons orbiting around as well if you keep your eyes open. The rings are kept really thin because the particles are always bumping into each other. And if a particle was on an orbit that was tilted too high, it would bump into the rings on its way through the rings, and it would be averaged out. So over time, they all agree to stay on the same plane. Even though these rings are enormous, they're only about 30 feet thick for the main rings. It's such a human scale, it's unbelievable. It's only 30 feet thick. Right. If you were to enlarge a piece of paper to the size of Saturn's rings, okay, it would be almost 4,000 times too thick. Right? These rings are really thin. There are moons that can orbit inside the rings, right, and outside of the rings, and their gravity can gather up any ring particles that get in their way. So let's call this a gap moon because it makes the gap in the rings. Okay? And as it orbits through here, it cleans it out or gathers up any particles. You can see its gravity leaves a little bit of a wake here. And the other part of the wake is on the other side here. Now it's weird when you think about a wake of a boat. The wake is always behind the boat. But here you have half the wake in front and half the wake behind. Right? It's because the moon is going faster than the outer band of the rings, but the moon is going slower than the inner band. And so in one case its effect gets ahead of it, and in the other side of it the effect gets behind it. Moons can also be called shepherd moons if they keep a thin ring in line. So this is called the F ring. And if any particles stray out, it gets gathered up by Pandora. And then if any particles go in, they'll get gathered up by Prometheus. Right? So the F ring's always losing particles, but it's always kept looking like a narrow ring by these two shepherd moons. And you can see a little bit of that gravitational wake here from Prometheus.
I think the F ring is Saturn's weirdest ring. We have a new analysis of images obtained by Cassini that show the F ring is actually even more dynamic than we thought. And for the first time, we can see some of the havoc wreaked by objects about a kilometre in diameter. This movie shows the trail of one of the 500 or so tiny objects that we see punching through parts of the F ring. We've highlighted the area where these trails can be seen. There's a little serendipity involved. We're actually concentrating on Prometheus. And what we didn't notice at the time was one of these tiny little trails has sort of sneaked into the field of view. But now we've done things a bit more methodically. We've actually looked at about 20,000 images, and we found lots of these little guys, and some of them we just caught in the act. So far we've seen about 500 of these objects in the Cassini images. Some of them may even be the same object. What's important about these images is that these little guys are the missing link. We know what Prometheus does. Prometheus creates channels, ripples, snowballs in the F ring. But what we didn't know is what happened to these snowballs after they were created. We know also that Prometheus can probably destroy some of these things, just like it can create them, can also change their orbits. But now we've got evidence that some of the little guys actually survive, and they go on to punch through the F ring on their own. Even during the time that Cassini's been at Saturn, the F ring keeps changing. It's the only thing you can rely on in the F ring. Every time you look at it, it'll be different.
The last thing I will share with you about Saturn's rings is something weird that we found. So here's a little movie, and you can see that the rings are rotating counterclockwise. And these particles down here are closer to Saturn, so they should be going faster. And these particles out here are going slower. So if there was any pattern that existed across the whole ring system, you should see it getting skewed. As these particles get ahead, it should pull that part of the pattern ahead. But we do see these dark regions, we call them spokes, and they don't wind up that way. They don't get pulled and stretched by the rotation of the rings. So what are we left with? We think it's magnetic fields. And the magnetic fields punch through the rings and can change the alignment of the ice crystals and can change the reflectivity then. So an ice particle might rotate into a region of more magnetic field, get turned, and then rotate out of the magnetic field and randomly orient itself again.